Hello everyone and welcome back. In today's video, I wanted to show you a shortcut method that can be used to find the partial fraction decomposition of fractions like this one really quickly. And the name of this shortcut method is the Heaviside cover-up method. And we'll see why this name is very nice and accurate in just a moment. So to demonstrate the shortcut, I'm going to show you how it works with this same fraction that we decomposed in the episode from earlier. We decomposed this fraction 1 over x squared minus 5x plus 6. And we found, just to note, we found that the values of a and b were given by -1 and +1, respectively. Let us see how we can obtain these same values without having to do any of these steps of clearing the fractions and setting up a system of equations to solve for a and b. Now, step one of this process, factor the denominator and set up the template. So here, the denominator factors as 1 over x minus 2, x minus 3, and the template for the decomposed version on the right side is some unknown number a over that first factor plus some unknown number b over that second factor. So now suppose that I was interested in finding the value of a. If I wanted to find the value of a, this is how we can do so quickly. First, find a value of x that zeroes out a's denominator. Cover up a's denominator on the left side of the equation and plug in this x. What results from this process is the value of a. So that's a lot to process, so let me show you what I mean. Suppose that I wanted to find the value of a. The first thing that I would do is I would ask myself the question, what value causes the denominator of a to vanish? So looking at the denominator of a, this denominator vanishes when x is equal to 2. So I'm going to take that value, x equals 2, and I'm going to bring it over to the left side of the equation. And I'm going to cover up a's denominator, which is x minus 2. And I'm going to plug this value of x into what has been left behind after that factor's been covered up. And I get from that a is equal to a numerator of 1 divided by an x minus 3, where specifically I have plugged in a value x equals 2. The result of that is, after simplification, that a is equal to minus 1. And wouldn't you know it, that's exactly the same value of a that we found in yesterday's work via this longer process here. A was equal to minus 1. You can do exactly the same thing to find all the other values. Repeat for all the other constants. So for example, next thing that I need to do is find the value of b. So what I'm going to do is I'm going to go into my template and I'm going to ask myself first, what value of x causes this denominator under b to vanish? This denominator vanishes when x is equal to 3. So I'm going to bring that over to the left side of the equation, the heavier, bulkier side of the equation, and I'm going to cover up the factor x minus 3 in that denominator. And then I'm going to plug x equals 3 into what has been left behind. So I get that the value of b is equal to 1 over x minus 2, here 3 minus 2, and after simplification I find that the value of b is positive 1. And wouldn't you know it, that's exactly the same b value that we found earlier by this more complicated and involved method. Now that you know the values of a and b, you're basically done. The only thing that's left to do is put those values back into the template. And as we already saw yesterday, this would be the decomposition of this fraction. Now, I have written out all these steps in full just to really make sure that it's clear to you what I am doing. But in practice, most of these steps are done in your head. And so that can make this process of finding a partial fraction decomposition go really, really quickly. This method is also extremely advantageous if you are working on a fraction that has a lot of factors in this denominator. For example, yesterday we worked with the fraction 3x plus 1 all over x cubed minus x. And we remember from the previous episode that the process of decomposing something like that was kind of involved because you had three fractions, which meant that we had to solve a system of three equations to find these three unknown constants here. Let me show you how the shortcut can be used to find these same three values, but much faster and more efficiently. So the game begins the same way as always. I'm going to start by factoring my denominator and using those factors to set up a template over here on the right side. Now I'm going to use the Heaviside cover-up method to help me to quickly find the values of a and b and c. So starting with a, I see that this denominator vanishes when x is equal to 0. So I'm going to bring that over to the Heaviside, and I'm going to plug that in to the Heaviside where that copy of x has been covered up. And so I get that a is equal to 0 for x here, 0 for x here, 0 for x here, 3 times 0 plus 1 all over 0 minus 1, 0 plus 1. And so the result of that calculation is 1 in the numerator, negative 1 in the denominator, a is equal to minus 1. Wouldn't you know it, that's exactly the same result that we found using the longer method from earlier. Let's go ahead and find the value of b using this same process. To find the value of b, I will start by thinking about what value of x causes this denominator under b to vanish. And that such a value of x would be x equals positive 1. So I bring that over to the Heaviside. I cover up that denominator on the Heaviside, and I plug x equals 1 into what remains there. And so plugging x equals 1 into what remains, one replacing x in the numerator, one replacing these x's in the denominator, I get 3 times 1 plus 1 all over 1 times 1 plus 1. So in the numerator 4, in the denominator 2, and so what you can see is this value of b aligns perfectly with the b value that we calculated for this problem yesterday, that we calculated b equals 2 after the correction. And finally, if you want to get the value of c, once again, you just repeat this process. Starting out, we think about the value of x that causes c to vanish. That would be x equals minus 1 in this case. I'm going to bring this over to this sort of heavier side of the equation. I'm going to cover up that denominator, and I'm going to plug x equals minus 1 into what results here. So the value of c we get by plugging x equals minus 1 into all of these different positions. And so in the numerator, we get 3 times minus 1 plus 1. And in the denominator, we get x equals minus 1 times minus 1 minus 1. And so that looks like negative 2 in the numerator divided by positive 2 in the denominator. Yes. And so for c, I get the value of minus 1, which again is the same one that we got before after the correction. So in my opinion, much faster method, much faster method. I didn't have to set up 3 systems of equations for 3 unknowns. In my opinion, also a much safer method. You know, in the previous video, I did make a sign error here, right, that I had to correct. The only reason I realized I made this sign error is because doing this method, I realized I got a different value for b. So doing this method actually got me the correct answer, whereas doing this method, I ended up making an algebra mistake that got me the incorrect answer. So in my opinion, this method is just better across the board whenever it can be used. The only drawback of this method is that it really can only be used with fractions that have this quality of having distinct linear factors in the denominator. We will not, unfortunately, be able to use the Heaviside cover-up method to help us with the fractions that we will be working with in the next episode. We will have to use in the next episode a technique that's a lot closer to what we did in the previous video.